CHEM104. This is lab. This is number one, isn't it? This is the first lab we've done? Yes. Number one. Chemical kinetics. So, and this is 13 February 2023. Yep. That was starting to lose off too. We also have it here to choose from. How about this one? Let me clean up this mess. Get the lab out. Now I assume that you've all prepped your notebooks. And I'll wait to check notebooks until we go in the lab because we got two ladies that are coming in later. But we'll talk about the procedure now. We got pre-lab questions. Everybody do the pre-lab questions? No. Okay. So let's start there. We'll do the pre-lab questions. All right, pre-lab one. Pre-lab cues. A container of household bleach has 5% sodium hypochlorite. So we're given 5% sodium hypochlorite by weight. So what does that mean? If it's 5% by weight, we're saying 5% weight. That is, for every 100 grams of sodium hypochlorite solution, for every 100 grams, 5 grams of that is this molecule. Okay, that's what that means. We're also told that the density of the liquid is 1.08 grams per milliliter. All right, do we need the density? Well, it depends on the question. Calculate the molarity. You want to know the molarity of that solution, right? This is weight. This is moles volume, right? Or mass. Maybe I should have done it that way. Legacy is the way I learned it. Kind of sticks with you after fun. Okay, so we can find the mass eventually and determine the moles of that, but we need to know what is that in terms of volume. Right? So that's why we need density. We've got to relate mass of the solution to the volume of the solution in order to determine molarity. Okay. So this is 5% solution. All right. Let's see, I'm missing something here. Okay. So 5% means what? It's 5 grams. Let's see, do it this way. This is a dimensional analysis problem. 5 grams of sodium hypochlorite per 100 grams of solution. Okay. So what we need to do is find out, first of all, we're going to find out how many grams per liter that is, and then we'll convert the grams. But we could do it, we could do the whole thing in just chain the conversions together. Yeah. So grams of solution, we want to find milliliters of solution. We would use this one, right? So 1.08 grams of solution per milliliter of solution, right? So now we've got grams per milliliter. We need grams per liter, right? Because this is moles per liter. Moles per liter. So we need to change this into liters. How many milliliters in a liter? Because milliliters here is in the denominator, has to be the numerator here. 1,000 milliliters per liter. So that is, now we've changed the denominator units to liters. Okay. Now we need to swing around. Now we need to change the grams of sodium hypochlorite to moles. So we need grams on the bottom because this one's on the top, and moles on the top because that one's on the top. So what's the molar mass of sodium hypochlorite? Well, you look it up. Calculate it. Sodium is 23 rounded to 2 decimal places. And oxygen is 16. And chlorine is what? Don't remember. I remember. 35, 45. So it's 74.45. There we go. That cancels grams and leaves us with moles on top, liters on the bottom. So that was the thinking part. The rest is number crunching. So we need 5, enter, 1.08 times, 1,000 times, and 74.45 divided. So I get 72.5 molar. Oops. What did I do wrong? Oh, I forgot to divide by 100. I did this way and then down here and left that one out. So it's 0.725 molar. There we go. See how easy it is to make mistakes. So that would be question number 1. So for this method, I assume you've read it, the bleach that we're going to use is not 5%, but it's 6%. So all you have to do is substitute 6 in here. You got your value. That's the full strength bleach. Right? We're going to dilute it. So you have a dilution factor in there that has to be incorporated once you know what the dilution factor is, right? Because you can't use full strength bleach. In our project, I think 2 seconds and all the blue dye's gone. Right? So it's got to take some time. So you'll dilute it and you'll determine the dilution factor experimentally. Right? That's part of the procedure. You have read that much. Okay. Good. So that's question 1 of the pre-lab questions. And the reason that we did this in pre-lab is so that you know how to do it for the lab. Only it's a different concentration. That erases nice. Except for that one. Okay, number 2. Yeah, number 2. Okay, number 2. How many grams per liter of sodium chloride are required in order to prepare a solution with a concentration equivalent to the solution in question 1? Why do we need to do that? Why do we need an equivalent molar concentration of sodium chloride to the bleach? No idea? Well, think about it this way. You've got this blue molecule in there that you're bleaching, right? And when you add bleach to it, you change the ionic concentration of that mixture because you're adding sodium and hypochlorite ions. Okay. So if you want to compare apples and apples, the ionic strength of that solution has to be the same for the second part of the experiment, where you take half concentration of your bleach. You can't just put water in there, because that would also dilute the ionic strength of the solution. So we replace the missing bleach, half the bleach. Now we replace it with sodium chloride, because that has no bleaching effect, but it has the same ionic strength. Right? So we need to find out, how do we make the same concentration of sodium chloride to the 0.725. So here's the setup: 0.725 moles of sodium chloride per liter. That's what we want to do. That's the mole. Actually, this is our equation. Molarity equals moles per volume, but we have to calculate the, actually that one works. That one works. Right? If we're going to have the same molar concentration of sodium chloride as we do hypochlorite, then we just substitute sodium chloride in there. But now we have to convert that to grams per liter. The question is, how many grams per liter of sodium chloride? So we already got our volume. What we need to do is convert sodium chloride to grams. Right? So moles, grams. So how many sodium chloride? It would be 23 for sodium, right? Is that what I said? And 35.45 for chlorine is 58.45. And that will cancel moles and leave us with grams per liter. If I did it right, it should be 42.4 grams per liter of sodium chloride. And that would give you exactly the same ionic strength, the molar strength of sodium chloride as sodium hypochlorite. Now we know that's true because what? When this one breaks up in solution, what does it make? It makes one sodium and one chloride. When sodium hypochlorite breaks up in solution, what does it make? It makes one sodium and one hypochlorite ion. So you make the same number of ions in solution. That's why we can say, okay, this molarity for that molecule is the same as this molarity for that molecule. It's not like we had something that would break up into 3 different ions, then we'd have a problem. It was a more complex problem, but it's solvable. So for the actual experiment, you'll need a different value here, right? For 6% hypochlorite, sodium hypochlorite. You need a different value here, but the same procedure will be used. In fact, I've already got stuff made up. But the sodium chloride solution is already made. So you can copy it off the bottle. Okay, number 3. Let's see. In fact, if we do that same calculation, 6% sodium hypochlorite is, let's put it right up here, 6% sodium hypochlorite is equal to 0.878 molar. Right, and that's going to be the concentration of our sodium chloride also. It's on the bottle. Number 3. What is the percent of sodium hypochlorite by weight for a liter of bleach that is 0.8 molar sodium hypochlorite has a density of 1.09? This is another dimensional analysis. So we're starting with 0.800 molar sodium hypochlorite, which is moles per liter. And the question is, what's the percent by weight? So we want to know percent. There I go again. Wait. So in order to do that, we work backwards from the problem number one. Okay. How do we change moles to grams? Well, we need our conversion factor in grams. Right, 7445 here. That gets rid of moles, leaves us with grams of sodium hypochlorite. Now we want to convert this to grams of solution. So if we know the density is in terms of milliliters, that has to be changed to milliliters. Liters here, milliliters there, 10 to the third. So I don't know why I did that. That gets rid of liters, leaves us with milliliters. Now we can get rid of milliliters and leaves us with grams of solution. Solution. This is solution. This is solution. And this is solution. So it's 1.09, I believe, grams per milliliter. And all of our units cancel and leave us with parts per 100. Right. Oh, no, we haven't done that yet. That's 100. That's percent. Yeah, that's right. Okay, now let me see if I did that right. And just do the calculation. 0.8, 74.45 times 1,000 divided 1.09 divided in 100. We get 5.4, 5.46. Rounded off 5.5. Yeah, that's a rounding error. I would have expected 5.5 because of my nose, but that's okay. Okay, that was all the pre-lab problems. Yeah. Okay. So, do we need to talk about aspects of the lab? No more pre-labs. So what are we going to do? We've got a reaction here. And actually it helps to write the rate law. The rate law determines everything that we're going to do. We're after the rate law, which is a K value times the concentration of blue dye, blue number 1. I used to have blue and red dyes. When the class was bigger, then half the class could do one, half the class could do the other. But with a small class, we'll just stick with blue. So that term, and then we got a value there. And then we have bleach, or sodium hypochlorite, actually. We want to know the actual concentration of sodium hypochlorite to its order. That's what we're aiming for. We want to find this and that. Okay. So how are we going to get at each one? This one's fairly straightforward to getting the concentrations of this term because we just calculated what the molarity of 6% sodium hypochlorite is. So when you dilute it, you just incorporate that dilution factor and that'll take it down to whatever value it is. And that'll be two different values because we're going to do the experiment twice. Once for the high concentration, one for the half concentration. How do we get it? This one. We're going to substitute into this rather than the concentration of the what we call the chromophore, the molecule that gives us the color. We're going to use absorbance. So we need to know something about absorbance. So instead of putting the actual concentration here, we're going to have the absorbance of blue dye to the end now. All right, so we need to know something about how spectrophotometers work. Okay, and there was a discussion in here about that. Remember that, the Beer-Lambert law? Okay. Hey. Yeah, the Beer-Lambert law, sometimes it's written like this. Well, when you first walk up to a spectrophotometer, depending on which one you're using, you need to be sure that the units that you're measuring it in are in absorbance units, because they'll also have transmittance units, percent transmittance. And those are two different scales. So be sure you have the absorbance unit. The absorbance units are a logarithmic scale. And in fact, actually building the logarithmic scale into the machine straightens out the curve, makes it linear. Transmittance would be we don't want that. So we use absorbance. Beer and Lambert were two people that contributed to this thing. Absorbance equals, I think your text puts it like this. It's got that little E and then a B and then a C. So the E is a term called molar absorptivity. Now this is the law, the Beer-Lambert law. We don't have to deal with that. I'm just giving you that for information. That's this one. B is equal to path length. And C equals concentration. Okay, so notice that if the path length gets longer, gets bigger, absorbance gets bigger. Our path length is standardized at 1 centimeter. The cuvettes, that's what we call those little tubes that we're going to use. The cuvettes are 1 centimeter, exactly 1 centimeter path length. So we don't have to worry about that. That stays the same. This molar absorptivity, that's constant also. This is constant, that's constant. So these two terms become some sort of constant. And what we're going to do is, as the concentration of our blue dye changes, the absorbance is going to change. Okay, and that absorbance value is what we use to measure concentration. The absorbance is going to start out here and it's going to go down over time. So that's what we're using. The absorbance units are key to the concentration. Okay, all right. Let's see. Some more pertinent information here. Flip a couple of pages. I'll come back to that. It'll make more sense once you have data. Okay. So I might have mentioned this last time. How do you get at the, we're not going to have, well, yeah, we are going to have initial rates. We're going to have rate values for two different experiments. But we're going to, this is not strictly speaking an initial rates problem because we're letting it progress all the way to the end. And that's one of the reasons that we use a blue dye, because once it's been destroyed by the bleach molecule, the chances of the products coming back to be a blue dye are almost zero. So we've got an initial rates all the way to the end. But We can't get at the order of one if we let the other one vary. So what we do is we make this concentration so high that it essentially doesn't change during the reaction. So what happens there is the rate now becomes, let's take this one and put this one over here. Oops. Sodium hypochlorite to the M. Now times the absorbance of blue to the N now. Okay, we make this one so high that it doesn't change. So what do we call something that doesn't change? Constant, right? So these two together now are going to represent this pseudo rate constant. And that's the one we're going to get first. There we go. So we get a rate value and against this concentration, and there's a pseudo rate constant involved. So how do we know? Yeah, how do we know? Since we're going to have to graph concentration versus time, which means what? That's the integrated rate law, right? The one that has a time factor in it. Right? This one doesn't have time. We need one that has time. So the integrated rate laws, we need to take our raw data. Did I mention this before? Set up a table. If you can do it in Excel, it's a lot easier. So you'll have a time here, and then you'll have concentrations. For this one, you have blue there, and you'll have values here. Then you'll have the natural log of A over here, and you'll have 1 over A over here. Right. Set that up in your spreadsheet and have it do the calculations for you. Or you can do it by hand, whichever you prefer. And then you plot this group, right? Time against that one, plot this one against that one, plot this one against that one. And which one's straighter? Or which one's straighter? Right? You'll have experimental error, so you're looking for the straightest. So you pick out one, which one's the straight one? Well, let's assume it's this one, say. Then this will be A to the first power. Okay. Then we would do the experiment again at a different concentration of sodium hypochlorite. Oh, and you can also use the equation, whatever the integrated equation is, right? But any one of those three integrated equations, and find out what K is. Because you'll know, you'll be able to calculate the slope of that line. The slope of that line is either what? K or negative K, depending on which one it is. Right? Once you have K, then you can ratio the two laws. Actually, you'll ratio this thing. What is this equal to? K prime is equal to K times this one. Oh, excuse me, that's again. Okay. And if you ratio, you'll get two different K primes because you're going to have two separate experiments. And this concentration will vary for the second experiment. So once you've determined the K prime, just like we did for this one, this would be for the first experiment, and then for the half strength bleach, you'll get another K prime, a different K prime, because you changed a concentration. So once you get the K primes, you've got a K prime for the full strength, and then you've got a K prime for the half strength of bleach. And that's equal to still the K, but now you have this other one. here. And you've been able to calculate the concentration of your sodium hypochlorite because we know the molar concentration of the original bleach and then the dilution factor. Okay. So the original dilution factor will give you this value. And then you just take half of it for this one. Plug in those values. Plug in these values and you ratio them, right? This one to this one, just like we did with the initial rates. Right? Once you get the data, it'll make more sense. And we'll go through that also. And then what stays the same? Okay. Oh, the K cancels out. Excuse me. These will be actual numbers, that one and that one. These will be actual numbers, that one and that one. K's cancel and leave you with this one as your unknown. And then you ratio them and say, all right, well, this number to that power is equal to this one. So what does the power have to be? Okay. It could be a whole number, it could be a fraction. I know this doesn't make a lot of sense right now because sort of talking in generalities. But that's the procedure. You're going to do 2 experiments at 2 different concentrations of sodium hypochlorite. And you're going to gather this bit of information right here. Absorbance of the blue dye in the machine as the time progresses. So somebody's going to be holding a stopwatch and say every however many seconds it says to do it. 10 seconds. And get that's your raw data here. And this will be for full strength bleach. And then you do it again for half strength bleach. Okay. So that's the first thing you have to do is decide how much bleach do you put in the tube to get a reasonable length of time that you can watch it. And then when you take half strength, it's going to be longer, of course. Okay. That's the mechanics of the experiment, doing those things. And then once you've got the order, let's see here. Once you've got the order here, then you can take the concentration of bleach and the K pseudo rate constant. It doesn't matter whether it's half, take individual, either one of these, but the value here and the K associated with it here and the power, then you can solve for K. That's how we get at the true rate constant. And then when you write your full equation here, you just say rate equals that value that you determined times absorbance to the whatever power times the sodium hypochlorite to whatever power. And that would be your rate law for this reaction. Okay.
We'll do that in the lab, right?
Well, yeah, if we have time. If we get started early, then we may have time to do it. Use the data that you get and do it. It's easier if you can access Excel. But if you do the manual, put it in your lab notebook like this and leave room to do these columns, then you can do those calculations. Just take the natural log of this one all the way across and then the inverse of that one. And then you've got, remember those empty pages on the left? You can draw a graph and plot them and see which one's strength. And that'll tell you the order of this one. Okay. And they should agree. You'll get this set for the full strength and a set for the half strength, and you should get the same order for the absorbance of the blue dye with either one. Okay. There's some quirky things that I'll have to watch for you, because if you absorbance, that equation, that I erased already. The Beer-Lambert law. It's linear within a certain range. If you get too high concentration or too low, it tends to flatten out. But if you're within a certain range, then it's straight. So if we get data that looks like it's doing wonky things at the ends, we just chop those out and keep the straight part, or the one part that behaves. All right. So I guess we take a little break and then migrate to the lab. Oh, Brittany's not here.
Do I need to sign?
Yeah. So Brittany missed the intro part. We probably ought to wait till she gets here. We mark this as lab also. So she's probably planning on not being here until when does the lab start? 10:30. Oh, that's 20 minutes. Well, see if there's anything else I can talk about. Clarify before Brittany gets here. Oh, we can talk about calculations relative to the bleach. Actually, I could save you some time if I just tell you how many drops to put in it. Instead of going through the process of doing like they say, 2 drops at a time, increase, and then when you get within, what is it, bleaches within how long?
3 minutes.
3 minutes, 3 minutes. Well, that's kind of a fun part too. When you do something like that, the procedure says, start off with this much and add 2 drops each until you get within 3 minutes. But I say, once you start off with, say, I don't know, 6 drops or 4 drops and get that data, then I'd jump it up to like 16 drops or 30 drops, or, start bracketing it in. And if you put in like 40 drops and it's way too fast, then, cut it back. And you can get there quicker by iteration than you can by slogging through each 2 drops. That's what I tell my class to do. But once you find out how many drops, one piece of information that you do need. Okay, once you find the number of drops of bleach per, I think it's 5 milliliters, right? Per 5 milliliters is in that tube. You need to go and take that number of drops and find the mass. You need the mass grams per number of drops. Right? And the reason for that is that's how you get at the actual molarity of bleach per drop. Then if you add, and in fact, this doesn't have to be, this can be any number of drops, right? It could be 20, 30, 40, 50, 100, right? As long as you know the ratio, what's the mass per drop, you need to know that, because that's going to relate to the density. And the density then will tell you how many grams of actual bleach you have. Okay. And when you do that, right, when you do that measurement, be sure you use the same dropper for the experiment. Okay, because those droppers are not calibrated. So you take a Sharpie or something, maybe make a mark on that dropper so you be sure to use the same one. Once you know the mass of so many drops, then you can calculate the moles of sodium hypochlorite per drop. That means when you add, say you add 10 drops to your mixture, that tells you you've added, you know how many moles of sodium hypochlorite you added to that mixture. And then the total volume, let's see, you also need to know, this one, the mass per drops, and you also need to know the milliliters per drop. So you would take that same dropper and take your volumetric, your graduated cylinder, the little one, the 10 milliliter one, and then you count the drops as you drop it in there until you get to a certain volume. Right? You can go all the way up to 10 milliliters if you want. And then you say, so many milliliters, let's say, just for argument's sake, it's 10 milliliters. And then you have, let's see, what would be a good round number here? So you have 150 drops. 150 drops per milliliter. Now you know how much, what volume is for each drop. Okay. If we were using volumetric pipettes or the, what do they call them? Eppendorf. If you're using Eppendorf pipettes where you push the plunger and suck up some liquid and then deliver it with those little plastic tips. Have you ever seen those before? Then we would know exactly how much we're adding, right? We wouldn't need to do this. But if we do it this way, measure the volume for so many drops, then we can find out what's the actual milliliters for each drop that you're adding. And if you know the milliliters for each drop, then you know actually how many milliliters of bleach you're adding. Because what's the total volume in your cuvette? It's what you added for the blue dye solution plus what you added this one. And you have to know the total volume in order to calculate the concentration. Okay, that's why we do that. So this 2 bits of information. You need to know the mass for a certain number of drops, and you need to know the volume for a certain number of drops. That needs to be, it may not have, probably didn't mention it in the procedure, did it? Did it mention it in the procedure? No, I didn't think so. So you do need to know that. And then you'll have enough information with everything else you've done to do all the calculations that you need. Actually, I've given these to you in the handout. That's part of the method. Right? Remember, did you see that one in the method? You didn't see that one? I need to give you a copy of that. Hold on. Okay, over here. Okay. That's no, it's not in there. It's a separate printout. Well, let me go see if I've already got printouts for that. I think I do. because I need one thing, I need the bleach calculations and the calculations for the final calculations for the K. So hold tight.
I have a question.
Yep.
Do we need to wait to do the post lab?
Yes,
Wait until after the.
you do the post lab after the experiment. Yeah. The pre-lab, we talked about that.
Mhm.
It's recorded. And your lab partner will probably have it written down somewhere.
I don't think we cheaper.
You see what you do?
That's not. This one, this one, here's the price. I don't even know what that means.
I'll look for him to draw. Spin the draw.
I believe, like, I don't know how to do that. I don't know how to do that.
Like on the data, I'll let her.
Oh, on the data,
You know, I'll have a page of that too. And then I'll let her the part. Because we have to draw guns for something.
well, but I feel like this,
Yeah, we have them there.
you know, but that's nice. Probably.
You fit like the one right here.
I was like gonna split this. But that's true. Okay. But yeah,
I want him to write this. Just it's down us like the last. This is
oh, that's so smart.
it's on the orders and then what's going to be displayed and what's so
Oh,
what's on the paper.
what is this?
We have to put the number of drops to get run 3 minutes or less.
Oh, wait, I put that all over here.
See, like in the procedure, it says stuff that we have to like put in the data. So I just circle what sounds like so many data, and I just leave it out of the procedure.
Well,
But you can, it doesn't matter. You can be like,
shoot. I hope I don't get like counter.
he's not okay. As long as you have it. And then that was just.
Oh, I put that here.
And then the absorbance value every 10 seconds. I think that's something.
I see. So I should have to just.
So yeah, that's just that. Yeah.
First. Listen.
Number of drops to get around 3 minutes or less.
No, put that there.
We're only using the board out when I use the
No, put that
okay. As long as you put it in data with the formula for it, might go. And I don't know this.
just to get a run Oh, I need to put that too. I said that you put that.
Oh, you don't have to. I mean, I'll just put it there. So I'll have it right there.
Yes. Yeah. What was the one that you said you put here about the drop searching?
The number of drops to get around 3 minutes or less.
No. Oh, this.
Oh, we have run time every 10 seconds. We've like a lot of it, I guess.
Thank you. You start the homework.
The signature. I did the one that was doing the same, but I haven't started like the most recent. Yeah.
What was the one?
First two of those. For the first test.
That's not the first.
Yeah.
Yeah, 10 and 11.
Yeah.
Yeah.
So
So 12 is 49 questions. And I started it. Yeah.
Was it?
Next Monday. I started it and I was like, I can do this. And I was like,
Maybe. Here.
It's called. Yeah, it's like one question, but like. Yeah.
This is the bleach calculation.
Same. So I can help you. I'm sure you mentioned, but no, I figured out how to do the other question. So I can.
You have copies of that, don't you?
Let's take the video.
But. Yeah. Oh, like the actual lab.
You got me really looking forward to it.
Yeah.
That's how you find the K value of the rate.
Thank you.
We shouldn't.
Okay, this.
Yeah, I figured it out. So whenever I get the homework.
So if you look at the, if you look at this, this was extracted from an Excel spreadsheet. If you look at the calculations that are done here, you'll see periodically bits of information that you don't have unless you do these two steps. And you'll see where they fit in here. And then the second sheet where we talk about actually finding the K, I go through that step by step, and the K prime is that pseudo rate constant. And the K prime is equal to that true K times the concentration of the bleach to the order, the power. So that's why you have two of them down there toward the bottom of the first page. You see the ratio of the K prime full and the K prime half. That's what we're getting at. So the first thing you're going to do with the when you do the calculations with the blue dye information, you're going to determine the K prime for one experiment, and then for the half experiment, there'll be two different numbers. And then you'll be able to calculate the bleach, the actual bleach concentration from that first sheet that looks like a spreadsheet. And those values go into the full sodium hypochlorite or the half sodium hypochlorite. And I give examples there. Actually, I took those examples from a real experiment that asked. And fortunately, that experiment was a good one because we got a whole number for the order for bleach. Sometimes it doesn't, it's not that pretty. Sometimes it comes out fractionally. And then
on the last page, you'll see where we go back to the K prime is equal to the K times the sodium hypochlorite to the N power. And there you need your whatever prime value you get for one experiment and the bleach concentration associated with it. And it's ordered. Once you find all those things, now you have that equation in one unknown, and that's your K. You solve it for that K. And then you write the complete equation. Okay. That's about as far as I can go right now without real data.